Well, hi there guys. It's time for us now to have a look at some vector functions in the context of the series, the four-part series on vector calculus. Now, you may recall that in the last video of the last series on dynamics, we did look at vector functions, but those vector functions were vectors of force, and they had x and y components which were written in terms of time. Okay, if there was a variable there in the x and the y components, they were written in terms of time. So that's fine. But in this video we're going to generalize the whole situation to just general vector equations, and we won't be necessarily using time at all. In fact, we won't be using time, where x and y are written in terms of something which varies. It won't be time. We will be expressing the x and the y components of these vectors that we'll be dealing with in this video in terms of just a third parameter, as it's called, a parameter, not necessarily time, in fact not time, and therefore they are called parametric equations, and they're quite different from like the normal Cartesian equations where you've got y as a function of x, because in those situations x is what's called the independent variable, where you can choose any value you like within whatever values are available to us for x, and then y then depends on the rule worked out from the value of x which we have chosen as an independent variable. Okay, so x is the dependent, y is the independent, but in these particular parametric equations, both the x component of the vectors and the y components of the vectors are worked out independently in terms of a third variable or a parameter. Okay, so x is a function of the parameter, y is also independently a function of the parameter. That's why they're called parametric equations. Okay, and the objective of this video is to then work out the relationship between x and y, and then draw graphs of those in some situations. So having done that fairly long preamble, I really wanted to make the point to you clearly so that then we understand what we're doing. So let's just go through this now bit by bit. In vector functions, yes, we can describe the resolved rectangular components x and y in terms of another independent variable known as a parameter. Now, this is an example, but before I do that example, I'll take it away again. I want to say to you this: it's very, very important to use either the implied or the stated values of that parameter to work out the possible values, firstly of x and secondly of y, because in so doing that, very often it will be revealed to us through that process that we're ending up with restricted domains in our functions. Okay, and if you don't take note of the values that that parameter can have, and hence the values of x and also consequently the values of y, you might end up making a big boo-boo, a big mistake, because you might not see the restricted nature of the functions. This will happen in some of the examples I will show you, okay, and you'll see how interesting it is. So I'm going to be very, very careful to work out the domains and the ranges very, very assiduously, okay? So let's go with that. And now you know why I'm doing that, because of the restricted functions which can result. Now, okay, first example, first cab off the rank. Find the Cartesian equation for the graphs represented by the following vector equations. Now, in this case, as I said to you, as I foreshadowed, this t here looks like time. There's the x component, there's the y component, but this is a parameter. It is not time, because how can time have any real value? Because time can only be 0 or positive, can't it? Yes, according to the laws of physics and the laws of nature on planet Earth, it certainly can't be negative, so this t can't be time. It's just a parameter. However, we're noticing that t can have any value at all. It's unrestricted. Therefore, we would have an unrestricted value for the x component and an unrestricted value for the y component in this instance, okay? But it's very important to work through that process. There's x, there's y, okay? Now, we know that these have got a domain. This one, this x, the range, if you like, of x from the values of t, which is any real value, the range of x, domain of t, the range of x will be any real value, and the range of y, which is also an independent function of t, will be, what will that be? That would go, oh yes, it could be, well, that's a squared thing, so basically it will go from 3 upwards, wouldn't it? Just working it out, from 3 upwards, from 3 to infinity, including 3, wouldn't it? Yes. So that's okay, but it's more critical for us to work this baby out here, this one here, because the x is, when you do the Cartesian relationship, the x is the independent variable, which it's and the values which are possible for it come from the values that are possible for our parameter, and then that sets the scene for the y. Okay, I know I'm talking a lot, but you'll see as we go. So therefore, what I'm doing now, guys, is I'm going to, because we have to get the Cartesian equation for the graphs, we're going to eliminate t from one equation, substitute into the other in terms of x, and then we'll get our relationship between x and y. Okay, substituting into equation 2 that t is 2 minus x, and I get that, and I get that, and I get that there. Okay, alright, there she be. And that's all you need to do for that, where x can be any real number. Okay, yes, very good. Alright, number B, this is a tricky one, isn't it? Okay, now, again, t can be any real number here, it's not time, okay? So we better work out, particularly with these tricky things, this thing is likely to have some restrictions on it. Let's work them out. Okay, so that's the thing, there it is, and x is that, this is the x component here with the I vector multiplied by it, and the y bit is there, okay? Now, in order to get rid of time, I suppose we better think about, we'll think about the domains and the ranges in a minute. We're going to use what's called the fundamental theorem. I call it the fundamental, or the old faithful theorem of trigonometry, which is sine squared plus cos squared of a particular angle. In this case, t is behind the sine and the cos, so sine squared t plus cos squared t equals 1. Did you know that? It's very important that you know that because you use it all the time. So I'm making cos t the subject from equation 1, and I'm making sine t the subject from equation 2. Now I'm going to use the old faithful theorem, cos squared t plus sine squared t equals 1, and I'm going to substitute in for what I got over here, for what cos t was, this beastie here, and sine t is that. So I'm going to put them into that equation, and I'm going to get that. There you go. So x minus 1 squared plus y squared equals 1. That's a circle. It's got centre 1 and 0 and radius 1. Therefore, the domain is 0 to 2. 0 to 2. Now, if you go over here, you'll see that makes perfect sense because, look, the extreme values of cos t be minus 1 and 1. Minus 1 at the lowest point of its travel and in a vertical axis sense, and plus 1 being the highest point of its travel. 1 minus negative 1 is 2, and 1 minus plus 1 is 0. So therefore that makes complete sense in terms of its domain, right? Very good, isn't it? Therefore there you go, and that's the answer. Yes, are you happy with that? All right, very good. And you know that's just the way the circle works. Okay, it's basically got that domain, and the range will follow from the domain, and it all ties in. Okay, now let's go over the screen and do another one now. What do we got here? A Cartesian equation for each of the following: state the domain and range, and sketch the graph of each of the relations. All right, again, I'm looking at this very closely. T is any real number, so it's not time. T is any real number, so it's not time. So, okay, let's go for it. We'll put down A today. That's what it is, and the X is that. Yeah, now the X is going to go, if it's cos squared T, X is going to go naturally from 0 to 1. If you visualise a cos graph and then square it, you'll see the negative bits can't go into the negative anymore. They're going to be wobbling above the the horizontal axis, yes, and they're going to be oscillating between 0 and 1. And that's if, yeah, for any real value of t, that'll work, okay? Now let's have a look at y now. Y is sine squared t. Y will be oscillating between 0 and 1 again, okay? Makes sense, doesn't it? But it's really important to work that out, because I'll show you in a moment why it is important to work it out. You've got to work out your domains, guys, or the range of x and the range of y. The range of x is really, really crucial, because in terms of the Cartesian relationship between y and x, the possible values of x, e.g. the range in this case, the possible values of x become the domain of the Cartesian relationship between y and x, yeah? So, okay, there's our what do you call it, the Old Faithful theorem. There it goes, and we're going to get this, right? That's sine squared t, that's cos squared t equals 1. So therefore y is minus x plus 1. But we noted that x can only go from 0 to 1 inclusive because of this situation with this parametric equation here, right? Yes, see? Absolutely crucial. Now we have to do a sketch of the graph, don't we? Yes, we do. So there is the sketch. See, x is allowed to go from 0 to 1 inclusive. So it's a restricted y equals minus x plus 1, see? Because otherwise, if you just went willy-nilly up that way and willy-nilly down that way, you'd end up with something which was wrong, and you wouldn't get your full marks for it. You see? So go carefully and work out the possible values of x from here. Okay, and also while you're in the process of doing that, work out the y's for good measure to make sure it all ties together and you haven't made a mistake and no alarm bells go off when you're working the whole thing out in terms of y and x. Okay, that's really, really good advice, even if I do say so myself. Yes, that's the function. There it is. Everything's looking good now. Here's number b. Well, that's a very, very easy looking one. Again, I'm looking at this. T is unrestricted. So if T is unrestricted and these are just straight linear looking things, I'd say we've got no problems with any restricted domainy xy things here with this. I'll show you why. There it is, x is t. Therefore, if t can be anything, then x can be anything. So there ain't no restriction, guys. Pardon the double negative. Being a mathematician, a minus times a minus gets a plus. So there isn't any restriction on this one. Yes, that's correct now, grammatically and mathematically. So therefore the y is 1 minus t, and therefore if t can be anything, so can y. So this is an unrestricted one, this one. And now we're going to eliminate t. T is equal to x from equation 1, put it into equation 2, and you get y is minus x plus 1. So there it is, there's the graph, and it's unrestricted in this case, yeah? Very nice. Make sure you label your axes, put your intercepts in, preferably as coordinate points, and everything's good. Okay, you happy? Yes. You getting the idea? Yeah, it's just a systematic process. It's just a matter of getting used to it. Look, you can absolutely smash these if you do some practice. So, get ready to smash them. But we've got a couple more examples yet to go. Now, in this case, it looks like we're using lambda. Now, for something completely different, come on down, lambda. So for each of the following, state the Cartesian equation, yes, the domain and range of the corresponding Cartesian relation, and sketch each of the graphs. All right. Now, this is a second tan one. Now, they don't state anything about lambda here. They don't give you any domain for lambda, so therefore we have to take the implied values of lambda, okay? Again, the same thing over here. Yes, they don't give you any values for lambda which apply, so we have to take the implied maximum values possible values that lambda can take. So this one here, this was a second tan. I can tell you right here and now, Wolfman tells you this is going to be a hyperbola, because I've done hundreds of these. This one here is going to be, if there's coses in one of them and sine in the other one, it doesn't matter which is which, then it's either a circle or an ellipse, guys. If the coefficients of the cos and the sine are the same, it's a circle. If the coefficients of the cos and the sine are different, it's an ellipse. So this is an hyperbola, I think. This is an ellipse, yes. Now let's do it. We're going to be very careful with those domains, as I'll show you in a moment. I've got a little trick up my sleeve at the very end to show you one of these with some restrictions on the domain, and you wait till you see what happens. My goodness. It's a nice trick. So, okay, this thing equals that. Yes, all right, that's fine. Now, we'll just go each in turn. Here's the x, and we know that there's the y. Now, let's look at the possible values of lambda, and then the implications for the range, which is the x. And the possible values of x become the domain of the xy Cartesian relationship, yeah? Now, okay, now with sec, lambda can be anything. You know that, to infinity and beyond for these trig functions. Now, therefore, x, now if you think about that, I'm going to show you a graph in a minute. X, the range of this equation here, would have the possible values of all reals with the exception of the interval from -2 to 2 non-inclusive. I'll show you a graph in a minute and you'll get it. For the y equals tan lambda, again lambda can take any value except the asymptotes where it's undefined. So it'd be pi on 2 plus any number of periods forwards or backwards from that point, where that's how you express that. Okay, plus pi plus n pi where n is any integer. Yep. Now here's the graph. So yes, so therefore y, yeah, for tan y has any value. So that's the range of this one here, of this parametric equation here. Now, there's my graph. That is the graph of 2 sec lambda. This is x, this is lambda, and therefore x can go from 2 up and from -infinity up to -2 and back again, and then that's 2 up that way. So the only interval that x can't take is from in here, from -2 to +2, but non-inclusive, right? That shows you pictorially the values that x can take, right? Yeah, now here's your other one. Here's your y equals tan lambda. Lambda can be anything except pi on 2, and then plus or minus any number of periods from there. And you can see that the range is just this manic -infinity to +infinity thing which tan does so beautifully. Okay, now it's all tying in. You sort of get it now. But this is the crucial bit here. This is the crucial bit here in terms of the Cartesian thingy. X is allowed to have anything, any value except from -2 to +2, but non-inclusive. Now we're going to work out the relationship between x and y and eliminate the lambda bit, but you'll see that this will be the domain of the hyperbola, this r except from -2 to +2 non-inclusive. So here we go. Sec lambda, making that the subject, equals x over 2, and tan lambda will just be y. Just manipulated these a little bit over here to make sec lambda and tan lambda the subject. Now over the screen we're going to go now. That's where we got to. Now, the rule of trigonometry which applies when you get sec and tan is that 1 plus tan squared anything equals sec squared anything. So that's what we're going to use to our advantage. We're going to substitute into this equation here in terms of x and y. Okay, there's sec, there's tan. So 1 plus y squared equals x squared over 4. That's what you're going to get. Okay. Now remember, x, that was our domain for x, and we know that we also knew that the possible values of y being tan lambda were r. Yeah. Now let's go with it and see if it all agrees with what we've got, guys. Okay, that's a left and right shaped hyperbola, and if you look at the x-intercept, you make y equal to 0. You get plus or minus 2, and the asymptotes. To get the asymptotes, you neglect this 1. You call it 0. And then you solve it for y, and that comes out at plus or minus a half x. They are the asymptotes. Yeah, now here it comes. Da-da-da-da. Oh, look at that. Isn't that something else? Now, let's just check ourselves out here. Look, here. I said that x was allowed to go from all real numbers except -2 to +2 non-inclusive, and look, there it does. Look, the only bit where x is not represented is within this no man's land in here, from -2 to +2 non-inclusive, because it does have a value of 2 on the right branch and it does have a value of -2 on the left branch. Yeah, I know, it's cool as. Now we said that y should be allowed to have any real numbers, and it is. Look, it just goes, ooh, it's like Halley's Comet. Comes flying in here from +infinity, goes, ooh, and then goes flying down there to -infinity. So it does have all real number available for its possible values. Yeah, isn't it good? It's just beautiful. Beautiful. Now we're going to do this baby now, this one here. This was going to be an ellipse, okay? As I foreshadowed earlier, it is definitely an ellipse. Oh, yes, yes. This all works perfectly and beautifully. But you'll see in a moment why it's so important to be fussy, working out the possible values of x and work out the possible values of y while you're at it from the original parametric equations. Because things can go wrong if you don't. B for you and me. Here we go. There's the thing. And therefore x is that, and therefore y is that. Now let's go through the motions. What are the possible values of x, and what are the possible values of r? Lambda can be anything at all, because there's no stated value for lambda. So that means that x, if you work that out in terms of what cos does, it'll go from -1 to +3 inclusive. And if you have any possible values for lambda in here for the y parametric equation, you'll get this one here. Y can go from -3 to +3 inclusive, because the amplitude of this is 3. Okay, now, ooh, look at that. There's x. Yeah, x is this thing here. So there, it's an upside down cos with an amplitude of 2, and it's been vertically translated up by 1. So indeed, ladies and gentlemen, the range goes from -1 to +3 inclusive. So it's tying in beautifully. Now this one here, there's the that's the y component. So it was just 3 sine lambda, wasn't it? Yeah, so that's got a range of, yes, there's the range. You happy? Now, it's now time that we've done all our due diligence. Now we're going to get x in terms of y and see whether indeed it is an ellipse with these possible values for x, which become our domain of the Cartesian, and these possible values of y, okay? I think we have to, yeah, so making cos lambda the subject and sine lambda the subject, and using our old faithful theorem of trigonometry, that's where we got to. Now that's what we're going to do now, and we're going to substitute in terms of the right hand side here of each of these into that star equation, and it is a star equation. There it goes, and I can just manipulate this one round here and call it x minus 1 all squared, because it would be the same thing, and that is indeed, it is indeed an ellipse, no problem. Centre 1, 0, and the x semi-axis is the square root of this, which is 2. The y semi-axis is the square root of that denominator, which is 3. And there it is, guys. Look, look, look. Feast your beaties upon it. Look, it's got a centre at there, and it goes from x semi is 2, isn't it? So it goes back 2 to -1, and forward 2 to +3, and then the y just goes up 3, down 3, and it is truly a beautiful thing to behold. See, it all ties in. It all ties in, doesn't it? See how excited I'm getting? Now this one here, I made this one up to prove the point of why it's so necessary to do your due diligence, right? What have we got to do here, Wolfman? We've got to find the Cartesian equation which corresponds to the following. Now it's okay, this one here is a vector equation. Now there's your x component, 3 sec lambda, and the y component is 2. Oh, I should have put i's and j's in there. Wait a minute, I'm just going to fix it up, sorry. Abracadabra, I fixed it, okay? My apologies. Now, okay, let's go with this now. Now you'll see here what I've done. What Wolfman has done is I've restricted lambda now, so it can only go from pi on 2 to 3 pi on 2 non-inclusive, right? We've got to state the domain of the range and sketch the graph. Now, this is why you've got to do your due diligence. Ladies and gentlemen, watch this trick. Now, x is 3 sec theta. Now, oh, not theta, lambda, I mean. Lambda is allowed to go from there to there, non-inclusive. Now, therefore, now I work out from that x, the range of this parametric equation, aka x, which in turn will become the domain of the Cartesian y-x relationship, which we're going to get in a minute. It'll be a hyperbola, by the way. Now, x is allowed to go from -infinity to 3, and including 3. Now I think in order for me to prove that to you, I better do a graph in a minute. Y is 2 tan lambda. From that, lambda is allowed to go from there to there, non-inclusive. Now if you work that one out, you'll also come to the conclusion that y can be any real number. Wolfman, how so? Well, funny you should ask. Here's my graph. And I've got, what have I got here? I've got, just to get it in context, that's 1, that's 2 on the vertical. Now, that's basically x. Sorry about that, I had to fix that up. That's x and that's lambda. Now, if we're allowed to go from to pi on 2 to 3 pi on 2, then the blue graph, the red graph is the cos, just to get things into context, because sec is 1 over cos. This blue is the one we're looking for. So what are the possible values of x within this span here, from pi on 2 to 3 pi on 2? Well, you can see that this point over here is basically minus 3. So it's minus infinity to up to and including minus 3, like that. Okay, you see that, right? Now that's proves what I was saying up here, right? And isn't a picture worth 1,000 words? My goodness, is it ever. Now, here's the other one. There's the y for you. There's the y. Now we're dealing in this lambda region here, from pi on 2 to 3 pi on 2. So you can see quite easily that tan just does its manic thing and goes from minus infinity to plus infinity, come what may. It just goes berserk and keeps going from minus infinity to plus infinity repetitively, but in this case only one cycle of it. Alright, so therefore y does have any real value. Alright, now we've proved that. Now we're going to go through the motions. We're going to go through the motions now and get x in terms of y and come up with the hyperbola equation. Okay, so sec lambda made the subject. Tan lambda made the subject, yes, and over the screen we go, and we're going to recap what we had. Now we're going to go, there's the star equation, 1 plus tan squared lambda equals sec squared lambda, and we sub for sec lambda, tan lambda, from up here, the right-hand sides in this equation here, in the star equation, and we get this. Okay, now that's that, and that is most definitely a left and right hyperbola, and it is superbola, and the domain, according to our thingy that we worked out over there on the previous screen, the domain, the possible values of x is minus infinity to plus 3 inclusive, and the possible range while we were at it, even not that we have to do that, but it's a good idea to do it just to get your ducks in a row and make sure everything seems reasonable and everything makes sense, was R. Alright, R. Let's do this. Now we're going to sketch the graph now. We're up to the final finale here. It's a left and right shaped hyperbola. Let's get the equation happening here. We'll make the x-intercepts. It's centered on the origin, this thing. The x-intercepts, we're going to make y 0, therefore x is plus or minus 3, so that'll be coordinate points minus 3 and 0 and plus 3 and 0. Center is at the origin. Yeah, I said that, didn't I? The asymptotes, you make this thing 0, you solve it for y, you'll get plus or minus 2x over 3. Now here it comes, guys. Feast your beady eyes upon this, and they will transform into sources as we speak. Sources, look at that. It's beautiful, isn't it? Now, but this is the rub, guys. This is why you need to do your due diligence on the parametric equation, particularly for the x, to work out the possible values that x can take, right? Now, yes, have you got it? If you see what's happening here, look at this, look. Minus infinity to 3 inclusive, right? So therefore, that is where x can go from, right? That, not that, right? That's out of range. So therefore, there's x and there's y, and that still makes sense, but we're only dealing with the left-hand branch. Only the left-hand branch. Now I'm going to make, for my next trick, abracadabra, I'm going to make the right-hand branch disappear before your eyes. Goodbye, right branch. Nice knowing you, but you are not needed for our little show here today. Okay, there you go. That's it. So it was the left-hand branch of the hyperbola. Now my challenge to you, I'm not going to do it in this video, but my challenge to you is how would you restrict the original lambda domain of that parametric equation to get only the right-hand branch of the hyperbola? That is my mission, should you choose to accept it, to infinity and beyond, and you're a star, and huzzah, huzzah, you'll go far. Doing that and having a wonderful time, and I'm going to get out of here and I'm going to go and have a lovely cup of tea, and I'll see you next time. Hope you enjoyed it.